The inverse power method is a very strong method for iterating the eigenproblem and finding solutions. It provides both the eigenvalue and the eigenvectors. It's a little more complicated than the power method that was discussed in the previous lecture, but still it's straightforward enough to allow the viewer to understand the convergence proof and to see the shifting and sweeping. There is a further method called Lanczos method, which is even more complicated, more powerful, and harder to understand. And in the lab that we do, we have the ability to run that particular solver. But I like to clear up this inverse power method and show you exactly what it is. I'll review the notation in the next figure. We'll review the power method. Then I'll discuss the inverse power method along with shifting and sweeping. We'll do a numerical example. And then, when you're sufficiently battle-hardened, we'll do the convergence proof. We'll end up with several problems in our problem session. I'll just write down some of our symbols that we use just to refresh those in your memory. K being the convention for the stiffness matrix of a structural dynamics problem, and M the mass matrix. The displacement vector with U as an upright character is the nodal displacement vector. This W is an unnormalized displacement vector. It comes out as an intermediate step in our iteration process. When I use a superscript S as shown, then that shows that you're iterating and you're on the Sth iteration. The eigenvector that results, as shown here, might be the ith eigenvector, for instance, the 7th eigenvector. If it's being iterated, it will have, in addition, the superscript as above. The lambda here is the eigenvalue, the lowercase ith eigenvalue, that's the physical eigenvalue. The cap lambda is the shifted eigenvalue. Let's review the power method for a minute. For the special eigenvalue problem, it's relatively clear that you operate with the matrix on a trial vector and the process goes from left to right here. There's no inversion of a matrix involved. K times U, where U is the Sth iterate, will yield a vector which can, by proper normalization, be put in the form on the right. The S plus first iterate then is an improvement over the previous iteration step. Now if I explicitly write out the intermediate vector that's obtained, and think of this as a bunch of numbers here in the stiffness matrix and a bunch of numbers in the displacement vector, then this W is a vector of numbers. Over here, however, think of these as symbols on the right with a lambda and a U, and your idea is to try to equate those to identify what this eigenvalue should be. It's typically done by normalizing such that you have the largest component of the U vector serving as the reference, and when that is factored out, then the largest component is unity. At that point, you can identify then that the scale factor involved would be your improved estimate on the eigenvalue. That would be your S plus first estimate on the eigenvalue. Now this does converge, this process converges to the largest eigenvalue, lambda n, of the matrix K and its corresponding eigenvector. The way that we have found the eigenvalue here is a little bit rough in that it only uses the information from one physical component of the vector, namely the largest one, and then to some extent the relative size of the rest of the pack. But that's not as accurate as if you were to use a Rayleigh quotient for your estimate of your current eigenvalue value. So that would be your S plus first iterate. So it's recommended, if you really want an accurate estimate, to use the Rayleigh quotient. The inverse power method works in a similar way, but the matrix is first inverted. Here, when you had a physical problem such as this, which is the special eigenvalue form, you would then invert the K matrix, put it on the other side. At this point, it's helpful to move the eigenvalue lambda to the left side, and then this process, when iterated, will go from right to left in that direction. We would put a trial value in to this location, multiply by K inverse, and then find an improved eigenvector and eigenvalue pair on the left. I'll show the intermediate vector explicitly in this figure. We're going from right to left this time, and if this is a numerical expression on the right, then the intermediate unnormalized vector is also a set of numbers arranged in column form. Then that's to be equated to these symbols here on the left in the same way as we previously discussed the power method. Now this time you find that the method will converge to the smallest eigenvalues, lambda 1, of the original physical special eigenvalue problem, and its corresponding eigenvector phi1. I guess that makes sense. We've turned the matrix on its head here, and therefore the method seems to be looking for the opposite thing. The Rayleigh quotient would be a better measure of the scaling of the problem and gives a much better estimate of the eigenvalue. The inverse power method becomes a little more distinctive as we move into the general eigenvalue problem, and especially the shifted general eigenvalue problem. We'll do first this version of the general eigenvalue problem with the structural stiffness and mass matrices. If we invert the stiffness and bring it to the right side, and likewise invert the eigenvalue and put it on the left side, then our problem again maps from right to left, where we would put an assumed eigenvector in that location and calculate a new improved one. The entire right side would be known then at the outset, and you would be solving for the normalized eigenvector here and the improved reciprocal of the eigenvalue. So actually the procedure is the same as a special eigenvalue problem, and we still are indistinguishable really from the original Stadola concept. So the methods kind of look a lot alike still at this stage. And we do converge to the smallest eigenvalue and corresponding eigenvector. That we can prove a little bit later, so we'll take that as a fact for now, and probably not surprising because of the way we've inverted the K, but it's not quite as obvious this time because in this original eigenvalue problem here you have both a mass and a stiffness term, and not clear at this point, you know, mathematically, you couldn't immediately state that it was obvious that you got the smallest eigenvalue and eigenvector out of this physical problem by inverting the stiffness, rather than, say, inverting the mass and putting it on the other side. But that becomes clear later. We know that the inverse power method converges strongly to a dominant eigenvalue and vector. In this case, with inverse power, it's the smallest eigenvalue. Then to find other eigenvalues and vectors, it's useful to sweep, and that means to so remove from the trial eigenvector any component of the previously found vector that your method converges to what was previously the most stubborn, unwanted eigenvector, but now becomes the most wanted one. Well, I'll show that more in picture form here. that here is our general eigenvalue problem with a spectrum of eigenvalues on this real number axis below. The initial iteration would naturally converge to the smallest eigenvalue, it will turn out. And so after sufficient number of iterations, you will get the phi1 vector. And that would come from directly iterating this equation. The original trial vector would have been arbitrary and put in this location, and then the procedure would move from right to left in that direction. But now, if we introduce a sweeping matrix such that when you multiply it times any arbitrary vector, you then find yourself in a subspace that's orthogonal to the known eigenvector direction, then this iteration here with an arbitrary vector put into it will converge to the second eigenvalue and eigenvector, namely the one here, just by searching in a space that's orthogonal to the previously found eigenvector. Now you can do this sweeping in a sequential way, as Flamenhoff showed, and get about 6 eigenvectors before the round-off error starts to grow. And so it's often common with a start in a problem with the origin as a reference to perhaps find 6 such candidate eigenvalues. The sweeping that we have just done is quite useful and helps you get your 6 eigenvalues. But now, after you've got those in your hand, you wonder, is there a more efficient way to get perhaps 6 more? And the answer is yes, and that's called the shift. Here is our general eigenvalue problem, and we again are interested in moving from the right side to the left. We're going to introduce rather artificially then a number lambda 0 that will be a shift of the origin of reference on the real number axis. And then we will measure eigenvalues from that point with this shifted eigenvalue, capital lambda. The change in variables is that under this location for lambda, we introduce instead lambda 0 plus cap lambda. Now, the fact that I call this lambda 0 is suggestive. Let's suppose it lies somewhere on this real axis here, that shift point now is in fact physically like an eigenvalue, and it is your guess at the next eigenvalue in fact, because you're going to converge to the nearest eigenvalue to that shift point. Well, we move the known quantity here, this lambda 0, to the left side this time, and we're going to collect the things that we know over here. We know the 2 matrices involved, and we know the shift point, which we have chosen. Then we leave the undetermined shifted eigenvalue on the right, along with the mass matrix. Now, we were only able to move this shifted eigenvalue there, or this shift point, to the left side because this matrix multiplication is distributive. We've pulled out the lambda 0m and put it on the left side. If we now do the audacious move of inverting this entire parenthetical quantity and move it to the right side, and then move the inverse of the lambda, the shifted lambda, to the left side, we now have a form something like we were using before, where the process will proceed from right to left. And we're going to put our approximate vector in on the right-hand position here, and then proceed across and get a better estimate on the left side. This inversion here, as you can imagine, is not trivial. It's the expensive part of the process, and so you would like to shift as few times as you could in a problem, but it appears that an optimum way to do this is to shift once for every 6 sweeping operations, or in other words, every 6 eigenvalues found. So if you use inverse power method in a problem with, say, 60 frequencies that are to be found, you will probably use some 10 shift points, such as this lambda 0. I'll write down this general eigenvalue problem in inverse power form again, and then bring out the intermediate step. What I mean here is that the numbers have been inserted in these locations, numbers for a trial vector inserted here, and then the calculation of this W vector has been performed. If this was the S iteration, then we now have an improved S plus first approximation to this unnormalized vector. Over here we have symbolically the combination of the scale factor and the direction, which we then adjust by picking our cap lambda in our vector. And that's usually done by taking a unit normalized eigenvector u, which gives 1 over lambda to be the largest component in the unnormalized vector. Now when we do this, we converge to the smallest shifted eigenvalue, the one that's closest to our shift point, lambda 0. And we do start thinking of lambda 0 then as an approximate eigenvalue. As before in the power method, it's really more accurate to use a Rayleigh quotient for the best estimate of the physical eigenvalue at this stage. Now let's do a mental experiment of a typical situation where you're doing both shifting and sweeping. Suppose the eigenvalues are arrayed as shown on the real number axis. We have a region of interest shown by these vertical bars, and we're interested in finding the frequencies that are between those two limiting points. We don't know where these frequencies are on the axis at this point. It turns out there are 3 in that range. Then we choose lambda 0 arbitrarily with our current knowledge, just say at some random point here, lambda 0. When you do that and you carry out the iteration, you'll find that this particular inverse power iteration will converge after enough cycles to lambda 8 and phi 8. And so you will understand what this eigenvalue and eigenvector are. So now we have the 8th eigenvalue and eigenvector. We use those to help create the sweeping matrix S8, and with that we build it into the iteration process as shown here. Then that will clear out any possible component of that vector direction from any arbitrary trial vector. We proceed to the left and we converge this time to the next nearest eigenvalue to this trial, lambda 0. And this time we'll converge on lambda 7 and phi 7. Well, likewise, you now create a sweeping matrix that clears out this vector component. And then the question is, what will be the 3rd eigenvector that we will get? And when we look at the distances, we find that this one here outside the range, namely lambda 9, is actually closer to our shift point than the one we wanted over here, lambda 6. And so the conclusion is that it was kind of dumb to pick the approximate eigenvalue anywhere but the center of the range of interest, because you want to converge first to all the eigenvalues and vectors that lie inside that range and not do this spurious convergence to an eigenvalue outside the range. Similar comments could be made, though, in terms of larger problems where you have a given frequency range such as this and you want more than 6 eigenvalues. Then if you wanted 20 or 30 eigenvalues, you'd have to pick appropriate shift points distributed within that region. There's a certain amount of logic then that's done, especially in the commercial codes that do that automatically for the user. One of the commercial codes with an inverse power solver is MSC Nastran. And they do this shifting and sweeping process that we've been discussing. We do need, unfortunately, in the dynamics problem to invert a matrix, and that cost is similar to the cost of a static problem. So this is done really not by inversion, but rather by triangular decomposition as shown here. And if each such inversion is tantamount to a static solution, you can see why solving for 30 or 60 normal modes in a problem will be many more times expensive than an equivalent static problem. So we're going to have to decompose this for each new shift point. And in Nastran they sweep for 6 eigenpairs for each shift point, and they use sophisticated logic as to when and where to shift. Let's continue on discussing how MSC Nastran handles the inverse power method. The shifting involved helps with rigid body modes. That's not explicitly stated how, but you can imagine that if you're converging to a zero frequency, that might require special numerical handling. For instance, so you don't divide by 0. Also, if there are closely packed lambdas, you might be able to move the shift point among them or to either side. Likewise, to get higher eigenvalues, you could shift toward them. Now, the operational usage of the inverse power method in Nastran is to specify a frequency range and then give an estimated number of eigenvalues that would fall in that range of frequency. Now, the frequency range is given in hertz. If you guess perhaps there were 10 frequencies in that range, then the program can space the shift points accordingly, and those are done automatically. You could, in addition, specify the number of desired eigenvalues in that same region, and the norm would be to take 3 times the number estimated, but there are better defaults if you do not do that and just take the default of the MSC Nastran logic. I think it has to do primarily with what happens if you don't get frequencies in the range and how many frequencies it will find outside the range and some items like that. There's also an accuracy of convergence, and during my lifetime that has changed. The recommended number has changed, and so better just to take the default value again and let MSC Nastran choose whatever is best according to their current wisdom. Now let's do a numerical example. I'll use our friendly matrix that we've used before, namely the matrix with a lot of 5s and 2s. We will search for the higher eigenvalue. We know that they are exactly 1 and 6. Here's our friendly matrix. It's a little bit of a degenerate problem in that it's a special eigenvalue problem and only 2-dimensional. Our eigenvalue that we searched for is lambda. If we move the shift point to lambda 0 equal to 5, then we are close to the higher eigenvalue at 6. So we'll try to find that and its corresponding eigenvector. So let's solve that. We'll carry out a couple iterations. Here's the matrix. We have put it in the form, though, of the inverse power method, where we have done the variable transformation on the eigenvalue and converted to this non-physical shifted eigenvalue. That brings in the approximate eigenvalue 5 that shows up here, and so we get this matrix that we have to invert. By carrying out the operations here, we get this type of a matrix, which we then invert and put on the other side here. You can carry out these calculations on your own at your leisure. We've brought the non-physical shifted eigenvalue here to the left side, so the sense of the iteration now is going to be to go from right to left. So we're going to put an assumed eigenvalue on this side, And we'll start the iteration with a U0 trial vector of 1 and 1 in order to exercise all the physical degrees of freedom. We'll carry out the multiplication in the next figure, and here's our product that we'd like. Here's the numerical value. This corresponds really to that intermediate vector that I've called W. It's an unnormalized vector. When I normalize it in the following sense, then these numbers are to be equated with these symbols over here. So it's pretty clear then that the capital lambda, the shifted eigenvalue, is the reciprocal of 1 1/4, which is 8/10, and then the eigenvector, now in normalized form, is this vector here. This is moderately close to the true value, which in shifted form should have been 1, so we're off by some 25% on our shifted eigenvalue at this time. A second iteration follows straightforwardly by re-entering that normalized eigenvector and pre-multiplying by that inverse matrix as before. So we multiply out the right side and get this number here. Again, that is 0.95 times a normalized eigenvector. The shifted eigenvalue estimate is 1 over that, or 0.105, and then the normalized eigenvector is here. Now at this point we're only over by 5 parts out of 600 on the physical eigenvalue, so we're within 1% accuracy. The vector, however, is off by some 2 parts in 50 because the true eigenvector is 0.5 and then unity. And so there's a bit more error in that. If we were to use the Rayleigh quotient, we would get a little better estimate of the physical eigenvalue at this point. This is rather common, that the eigenvalue will be converging faster than the eigenvector. When I started teaching iterative methods for eigenproblems some years ago, at first I had trouble finding a proof of the inverse power method, and several authors have contributed. I'll quote Wilkinson's proof here, which is really for the special eigenvalue problem, and then you may want to look up some other references for the general eigenvalue problem. Wilkinson is quite taken with this method. He likes to call the eigenvector iteration part inverse iteration. And his feeling is that this method is best solving for the eigenvectors only. Now, in other words, he believes in this method as one where you already have some approximate eigenvalues. So you would use an eigenvalue solver separately. And indeed that is done in the Gibbons and modified Gibbons methods, where they actually use the vector iteration to recover any vectors of interest and yet use a separate eigenvalue solver. So that in that sense what Wilkinson is talking about is just a step removed. He's only interested in the perhaps 2/3 of the problem of the inverse power method. He's interested in the vector iteration and not so much what's going on with the eigenvalues. An interesting thing about the proof we're going to do is that you do choose an approximate eigenvalue that you found by some other way, and that there's an error vector involved. And rather than drive that error vector itself to 0, which is a common way to attack numerically approximate answers, in this case we continue to use that error vector, and there's some information obtained from it. So now let's go through Wilkinson's proof of the convergence of the inverse iteration. The problem is to find an eigenvector, say phi sub p, of the special eigenvalue problem. And we assume that an approximate eigenvalue lambda 0 near lambda p is known. Then that value is used in the equation, and if you put that value directly in here, not in the way of a shift, but just assuming that you have an estimate of lambda and you just literally put it into the eigenvalue operator, this really ought to have mapped into the zero vector. It's a little in the second form that I showed the eigenvalue problem, where you put all the operators on the left side of the equation. And if correctly done, it would map the trial vector into 0. But this time, since you have chosen an approximate eigenvalue, it's not the right one, there's going to be some error, which will make that a non-zero error vector. And I mentioned that down below here. Now, you might think, well, let's drive that error to 0 by making lambda become closer to the real eigenvalue, and that's not what's done. So this is a different kind of a convergence proof. It's kind of fascinating in a way. So now let's change our viewpoint from that of solving a set of linear algebraic homogeneous equations into solving a set of linear algebraic non-homogeneous equations. We can do that because the determinant of this operator matrix on the left is not 0. And that means you can solve this as a response problem because we have a non-zero vector on the right. Now, we've been treating this epsilon on the right as if it was an error, or it shouldn't be there, sort of, you know, bad boy, go away like you do with a dog or something. But no, this epsilon now we're going to treat like a legitimate driving force on the right-hand side. In fact, it will become our trial vector in due time here. So let's not bias our discussion yet. Let's say that whatever that vector on the right side, epsilon, is, we can represent it with a linear combination of the eigenvectors of this problem, because the n eigenvectors in this space will form a vector basis. And then we'll put some participation coefficients, c sub I, as the factors that show the general shape of this epsilon vector. Likewise, the solution we're going to assume can be represented by a linear combination of the eigenvectors, and the participation factors are these z sub i's. I think the viewer can see how the niceness of the set of matrices that we have called upon, which are typically the stiffness and mass matrices, what a nice problem definition that is, because we're guaranteed that there are orthogonal eigenvectors that span the vector space in question, which is an n-dimensional Euclidean vector space. And so we're able to represent both the error vector and the answer with a linear combination of eigenvectors. Now, if we put those into both sides of the equation, on the left we had the K matrix acting on the solution minus this approximate eigenvalue acting on the solution. Then on the right side we have the error vector. But all of those terms are merely sums of the eigenvectors themselves. And so first we make use of the fact that the quantity k phi for the special eigenvalue problem, which I've shown here on the inside of the summation, then becomes lambda phi for the eigenvalue in question. If it's the ith vector here, then it becomes the lambda I times phi I here. The lambda itself times these other terms is a placid operation. We just bring lambda inside the summation. Likewise, on the right side, nothing happens really of interest. So I guess the important thing was this operation right here. Then if you collect terms by bringing those terms on the right side over to the left, you get this parenthetical quantity that I'll underline here acting upon the phis themselves. Now this is a set of linear homogeneous equations at this point, and because the phi sub I, which are the eigenvectors in the problem, are all different, there's no way to sum those head to tail to add up to 0 as shown here. Therefore, each of these coefficients in the front must separately vanish. And at that point, you can solve for the z sub I, which is the solution participation coefficients, in terms of, over here, the error participation coefficients, as well as this denominator made up of the distance between your trial eigenvalue or your assumed eigenvalue and then the nearby eigenvalues lambda sub I. So let me use those participation coefficients for the solution and then feed into the series form of the solution here. So I'll just put in what we found out about the z sub I. As we move across the set of terms, we hit what will become the dominant term because the denominator here will be relatively small. We said that lambda 0 was an approximation to lambda p. Now indeed the participation coefficients on the error, the C1 and the CP on up through Cn, have arbitrary size, but we may say that they're all of order 1, let's say, order unity, that is. At this point, you may now formally realize that your epsilon, which we originally considered to be an error vector, can now play the role of a trial vector, just as it did in the power method. And we will even give it the symbol u, such that when we put an arbitrary vector in here, then we will carry out this process. And that will give us an improved vector each time we do this operation. And the solution that we've done here is in effect a factorization of this matrix, but we have a complete solution for the coefficients of these u now. Now, just as with the power method, each time that you iterate, you find that you enhance the one eigenvector, namely the one corresponding to the eigenvalue closest to lambda 0. That's because the denominator is small in that participation factor. And in fact, each time you do the iteration, you then multiply that factor over and over. And so the most near unwanted eigenvalue is going to die out. And this ratio you have here is a ratio by which the wanted eigenvalue is going to grow compared with the unwanted one. So actually this is the reciprocal of the way that I had explained this previously for the power method. But lambda p minus lambda 0 is a small quantity and is in the denominator of the coefficient for the vector phi sub p, whereas the nearby most stubborn eigenvalues have this other factor which is larger. So really this factor is the growth rate of the dominant eigenvector which we are getting, which is going to be phi sub p. When I spoke with my live class earlier last week, I realized I probably should have written out that series expansion divided by this denominator and then showed a small ratio such that the dominant eigenvector here grew as order 1. It did not grow at all, whereas the other terms died off in the ratio of the reciprocal of this quantity to the s power, where s is the number of iterations. So maybe I'll leave that as a out-of-class problem for the viewers to see how that goes. So I've shown the way that this number grows for the dominant vector, but I could have done the inverse argument to show how the unwanted vectors died. Well, Wilkinson extends this proof to the general eigenvalue problem, and there are other researchy papers available on the method. After you get your vectors, then it's no trouble to find the corresponding eigenvalue or any set of them by Rayleigh's quotient. So that's the recommended way to finish the problem. So this proof shown here has depended on getting initial guesses for eigenvalues and then at the end using Rayleigh's quotient. Wilkinson is very high on the inverse iteration method for finding eigenvectors. And here's a quote that I've taken from him, that inverse iteration is by far the most powerful and accurate of the methods I've used for computing eigenvectors. And remember, he's considering that a part of the total eigensolution. Inverse iteration with sweeping is the basis of the inverse power method. Inverse iteration is used in the givens and modified givens method to find eigenvectors after you have already gotten eigenvalues by a transformation method. Our first problem in the problem session is to find the second natural frequency of a mechanical oscillating system. We're going to use the inverse power method with shift. Here's the mechanical system. There are no forces on it, so it's the free vibration problem or the eigen problem. Here we have something that's a stiffness matrix times a displacement vector, then a mass matrix times an acceleration vector. We're only going to do one iteration here and illustrate the inverse power method. A hint is given that the second frequency omega 2 squared is near 3.0, but not exactly 3.0. Well, let's solve the problem. First of all, a general assumption for finding natural frequencies in normal modes is to assume harmonic motion, and here we use a complex exponential for that. So we put in the harmonic time dependence, and the two derivatives on the acceleration terms will cough out an omega squared term. We'll identify that as the eigenvalue. Then we cancel the e to the I omega t and are left with this algebraic problem rather than the ordinary differential equations that we just had. Then we'll do the shift and put in, instead of the physical eigenvalue lowercase lambda, we'll put capital lambda plus 3. We now move the inertia term that's multiplied by 3 to this position on the left side of the equation, and then we move the eigenvalue to the other side by subtracting off the lambda mass times displacement as shown here. Now we need to invert this matrix here and put it on the right side and ultimately bring the shifted eigenvalue to the left side, and I'll do that in the next figure. So we simplify the matrices on the left, bringing them into this single matrix, and then we invert that numerically, which I've shown over here, bringing it to the right side. Really what you're doing is multiplying both sides of this equation by the inverse of that operator matrix. Then we bring the lambda to the left side, and as repeated down here. And this is the equation to be iterated. we're going to put a starting value, a 0 value in this location, do this forward multiplication, and then move to the left. So the trial vector that we'll start with is this matrix with unity in both components. And that leads to the following expression, where here we've multiplied out the matrices on the right side. We can scale that by pulling out the largest component, which is -1, and leaves a unit value for the largest component in the normalized vector. Of course, that operation is a little degenerate, but it is interesting that you get a negative value for the shifted eigenvalue. When we solve for that, it's really the reciprocal, you get -1. The physical value at that point, however, is the shift value, which is here actually, and then the new value that we found, the actual shifted eigenvalue, lambda, is -1. So it adds up to 2. That gives us our frequency of the square root of 2, or 1.414 radians per second. And the vector that we found was from up above is this vector here. So after one inverse power iteration, we have this answer for the eigenpair. I'll leave it up to the viewer to solve the problem exactly and see how close this is to the exact answer. You can use a simple determinant approach for finding the eigenvalues. Our second problem has to do with the convergence using inverse power. It's a little bit of a wordy question, and it takes this entire slide just to ask the questions. Suppose you had a physical system with 100 degrees of freedom. I've plotted the first 5 natural frequencies on this real number axis. So we have numbers of 10, 30, 35, 40, and 60. The questions are, to which frequency would the power method converge if used directly? To which frequency would Stodola's flexibility formulation converge? That would be the, if you had K inverse, we're presuming you would iterate K inverse times mass. To which frequency would the inverse power method converge? If you shifted the origin to 45 Hertz, which lays here, to which frequency would the inverse power converge? If you did that and then swept the trial vector free of the converged eigenvector that had previously been found, to which frequency would you converge? That would be like the second converged vector, or the most stubborn one in not quitting on the first iteration. Now let's give a solution to this long-winded problem. The power iteration that we discussed was only defined for the special eigenvalue problem, so it's a little hard to interpret my question on this problem. Let's assume that the mass matrix is the identity matrix, so that K phi equals omega squared phi would be the problem at hand. And in that case, the power iteration on the K matrix gives the largest eigenvalue, which would lie off the chart to the right. Now the Stodola flexibility formulation was of the form that the phi matrix equaled omega squared, and then the K inverse, which was in fact measured directly as a flexibility times mass times phi. And when working with that problem, we found that the solution converges to the largest eigenvalue of K inverse times mass, which is the smallest eigenvalue in the problem, or in other words, the frequency equals 10 Hertz here. Inverse power, when solved for the general eigenvalue problem, would also solve to the smallest physical eigenvalue here. It would be the closest one to the origin as reference. On the other hand, in part C, where we shift to 45 Hertz, then the nearest eigenvalue found by the inverse power method would be here at 40. So that would be our first eigenvalue eigenvector pair. Then if we stay there with our shift point and sweep out the phi4 content from the trial vectors, we'll converge to the next closest eigenvalue, which would be this one here at 35 Hertz. Our third problem will make us think a little bit about the error in the iteration process and how these vectors converge. I'm proposing that there is a 100-degree of freedom system and that our engineer knows the exact value for the first frequency is at 120 Hertz. If you used inverse power directly on this problem without shifting, you would get the following sequence of frequencies as estimations found by the eigenvector normalization. And that would be the numbers 132, 124, 121.3. And I've asked this rather cryptic question to try to find an estimate to the second eigenfrequency, F2. So what I'm trying to get you to think about is that as I carry out the iteration and get these successive numbers, and you know that there's a most stubborn unwanted vector contained in there, can we infer what that frequency is corresponding to that most stubborn unwanted vector? And so that's how we're going to carry out our solution, is to look at the eigenvector error and see if we can infer that. Let me write out the error in the eigenvector for this inverse power method. This is a special case because there's no shift, and so in the earlier proof there was a lambda 0 that's set equal to 0 in this case. I'm going to factor out the denominator on the first participation coefficient, which was lambda 1, bring that outside a brace here, a square brace that extends over the whole solution. That puts lambda 1 then in the numerator of the succeeding participation coefficient terms. Each time you iterate, you raise that power to one more index number. I'm using n for a general index right now. That means that the most stubborn error term will be this one. And as you reach convergence, the others hopefully will be smaller, so we'll, for the moment, neglect these. If so, this ratio, lambda 1 to lambda 2, is the number that we're after. If you notice that the ratio of errors that we had turned out to be 12 parts on the first iteration, 4 parts on the second, and 1.3 on the third. That means that we're decreasing the error by a factor of 3 after each iteration. So this would make it appear that this ratio of lambda 1 to lambda 2 is 1/3. If that's the case, then lambda 2 must be around 360 Hertz. Now, if there are other stubborn modes that we're trying to drive out that are near 360, then you may have gotten a pair of error terms adding up to give such a set of terms here. And so for instance, you might get that same kind of error if you had the next frequencies, say at 400 and 500 Hertz, but at least 360 Hertz is a good estimate, and that's what would happen if there were only a single stubborn frequency that you were trying to drive out. So 360 is our suggested answer. My fourth problem in the problem set is just another rather routine problem. So we'll just take care of this one for bulk in our diet. Here's an eigenvalue problem. It has real symmetric positive definite matrices. It was, looking at it originally, a special eigenvalue problem. Estimate the lowest eigenvalue and corresponding eigenvector by 2 iterations of inverse power. And then give the best estimate available for the eigenvalue, considering that you're only going to do 2 iterations, and then start with this trial vector. Now you can tell that this came from one of my exams in my course at the university. So we'll just turn the crank on this problem. Here is the general form of the eigenvalue problem, although our mass was the identity matrix. The inverse power requires this form where we invert the stiffness. So we do that literally here, and then bring that to the right side, and by now I've eliminated the identity mass matrix in this expression. So we carry out the multiplication on the right-hand side to get this. We then normalize that vector by pulling out the factor of 5. And then we identify the scale factor here with the inverse of the eigenvalue. And then we have the normalized eigenvector. The eigenvalue immediately becomes 4.6. And here's our normalized eigenvector that we reinsert for our second iteration. So we multiply out the right-hand side here and then normalize it, shown here. We get an approximate eigenvalue, which I can find then, but I throw that away pretty much because the eigenvector, once normalized, lets us solve the Rayleigh quotient and then get our value for the eigenvalue shown below, and that's our answer. So that completes our problem and our problem set.